Hey everyone, welcome into lecture number 7. This is on September 19th, 2023, and we're going to cover in this lecture section 2.3 of the textbook. Section 2.3 is on formulas for differentiation. Remember, differentiation is the process of taking derivatives. So as I write this down, differentiation again just means take a derivative. So all right, let's get to it. We're going to basically work out formulas for a number of different derivatives that we're going to want to take frequently. Then we won't have to do the whole limit definition every time, but to develop the formulas, we do need to do the limit definition. So let's go through some examples first, and then we'll develop the formulas and maybe write down kind of a summary of some of them, and write down some theorems that summarize the rest of them, basically. So the first one, we're just going to kind of build up here in kind of level of complexity of the functions. Let's say that we have a constant function, so like y equals k, where k is a constant. Constant just means that the function is always equal to the same number. All right, so here k is a number, and we just say that y is equal to k. So in this case, the shape of the graph is, if it's just y equals k, and here's our xy coordinate axes, the shape of the graph is just going to be, if this is the height k, it's going to be a horizontal line, right? It's going to be a line that passes through this height k, and at every x value it's equal to k. Now remember that the derivative is the instantaneous rate of change of this line at any point, right? So if you pick kind of your x and then a nearby a, and you kind of think about the limit going back this way, you want to find the slope of the tangent line at this point, right? This point above x, and you want to see how that's changing. Just try to measure the slope of the tangent line using limits there. But in this case, the tangent line is the line itself, right? Whenever we have a line, our function, the graph of our function is a line, then the tangent line is, in fact, the function itself at that point. And the slope of this line, of course, since it's horizontal, is m equals 0, right? The slope is 0 for a horizontal line. So based on this, no matter what height we're at, what height this k is at, we can say that the derivative with respect to x of our constant function k should always be the slope of the tangent line, which is in this case the slope of the line, so it should always be 0. All right, and it turns out that that's always true. But there's another way to do this, and this is a way that we did it in class actually during the last lecture, and that is to actually use the limit definition, right? So if our function is f of x equals a constant, again, in this case, the constant is k, then we can plug this into the limit definition. We say the limit as x approaches a, just like we drew in the picture, of f of x minus f of a divided by x minus a. This is going to be the limit as x approaches a of f of x, which is k, minus f of a, which is also k. Right? The function itself doesn't care what the input is, it always gives back k. And so this will give us this ratio. Of course, k minus k is equal to 0, right? So I'm going to rewrite this down here. But the limit as x approaches a, this becomes the limit as x approaches a of 0 over x minus a. And even though the denominator here, even though this denominator does tend to 0 as x approaches a, the top is always equal to 0. And so this limit is equal to 0. Hopefully we're getting good with limits, so this all makes perfect sense to us, right? And so either way we do it, whether we think geometrically or we compute this limit using the limit definition, we're going to get that the limit as x approaches a of k, a constant k, is always equal to 0. So from now on, we can always say if we're given something, like we want to take the derivative as x, with respect to x, of something like the number pi. Well, pi, it might be, kind of a funny number, interesting number, but it's a constant, right? So the derivative of any constant is always equal to 0. Likewise, you'll see in the homework there's some kind of tricky questions where we might ask you something like, take the derivative with respect to x again, of a number like, say, 2 to the 57th power. Well, 2 to the 57th power, we'll talk about how we take the derivative of, say, x to the 57th power later on in this lecture. But right now, 2 to the 57th power is just a really huge number. It's very, very big, but it is a constant, right? And so every constant, the derivative is 0. It doesn't even matter how big it is. So that one's also going to be 0. Okay, so now we can take the derivative of any constant, and we're good to go. Let's now talk about the kind of first power function that we're going to talk about here. So consider this function. Let's say f of x is just equal to x. Again, if we want to think of this geometrically, which we'll do this one geometrically as well, and then we'll kind of stick with our limit definition after this. But if we talk about the function y equals x, we want to try to find the derivative of this, right? Well, this is, again, a line, right? This time the line is not horizontal, but y equals x is a line that passes through the origin and has a slope of 1. So the line y equals x looks like this. And some of you are thinking, as I just said that out loud, right? I said it's a line that passes through the origin and its slope is equal to 1. Well, the derivative, right, of any line is the slope, right? So it shows a bad color there. Make it yellow so it's a little more distinct. But at this point here, if this is our A, we'll look up at this point, right? We want to say what's the slope of the curve around this point? Well, this tangent line to the curve is the curve itself, right? So again, we have the same scenario where here the slope is equal to 1. All right, so geometrically that is our answer, but let's take, let's use the limit definition as well. So using limits, let's see what happens. Here we want to say, okay, the derivative with respect to x of x, according to our limit definition, this is the limit as x approaches a of f of x. I'm going to rewrite the whole definition here. F of x minus f of a over x minus a, which is equal to the limit as x approaches a of x minus a, right? The function is f of x equals x. So whatever the input is, that's the same as the output. And then it's always over x minus a. And here we see, of course, that the numerator and the denominator in this case are equal, right? And so those are going to cancel. And in a limit, we can always do this cancellation. And so this is going to leave us with the limit as x approaches a of just 1. And the limit of any constant, we know, is itself. The derivative of any constant is 0, as we just showed, but the limit of any constant is itself, right, as x approaches whatever. In this case, x approaches a. All right, and so here we've shown that, again, for every x, the derivative as x approaches, or the derivative with respect to x of just plain x itself is always 1. Okay? All right. I'm going to do one more example of a function, and then we'll talk about how to combine some functions. The book calls that building new derivatives from old. But let's do another example here. I'm going to kind of take a leap here. And instead, I'm going to skip x squared. Let's just say, let's do f of x equals x cubed. It's going to turn out that all powers of x are going to behave similarly. We're not going to really do this one geometrically, but they're going to behave similarly. So I'm going to use x cubed here as the example. And for this one, I just want to use the limit definition. So I want to say, all right, what's the derivative with respect to x of this function? Again, the function is x cubed. So I'm going to plug it into the limit definition, which again, I'll write out in all the details here. Limit as x approaches a of, excuse me, f of x minus f of a over x minus a. And so this is going to be limit as x approaches a of x cubed minus a cubed all over x minus a. All right, and so in this case now we can factor this numerator. So it turns out the numerator here is a difference of cubes, and this is something that we've gone over in class already. The difference of cubes formula says that this can be factored. Now let me rewrite the limit. Limit as x approaches a. So this can be factored as x minus a times x squared plus ax plus a squared. And then again, it's still all over x minus a. Okay, and so once we see this, now we see why, that's a good thing that we can factor this. We see here we have x minus a on the bottom, x minus a on the top. Those are going to cancel. And now we're going to be left with a limit that we can compute, right? So this is going to leave us with the limit as x approaches a of x squared plus ax plus a squared. And now we're plugging in x, so we're plugging in a for x here. This then becomes a squared plus a times a plus a squared. And this is, remember, a times a is just a squared again. So this is 1, 2, 3 copies of a squared. Okay, so actually what we found here, we got an a in our answer. We found that the derivative, so remember we have this prime notation, right? So if f of x is equal to x cubed, what we computed is that f prime of a, for any value of a, is equal to 3 times a squared. And so if we want to write this in kind of a formula involving x's instead of a's, we just have to swap out the a's in this formula, right, and put in x's. So our derivative of f of x equals x cubed is going to be f prime of x, the derivative, equals 3x squared. Okay, and so that's what we just computed using this limit definition. All right, so that everything that we just did is true. This is just for x cubed, but we can kind of see a pattern here. I mean, it's hard to see a pattern from one thing, but we've done a bunch of derivatives at this point. And what we see is that this power up here, this cube power, kind of, in the case of a polynomial here with just one term, this x cubed, this 3 kind of jumped out in front, so that jumped down, and in its wake, it left one less power upstairs, right? And so it turns out that this is always going to be true. This is always going to be true, okay? So here I'm going to write this one as a theorem, and we are just going to accept this for what it is, all right? If you go on in math, then there's lots of classes where you can, provide some arguments to prove that since this works for x, you can check that it works for x squared. You can check that we just did x cubed. You can check that it works for x to the 4th. You can show that it'll work for any whole number power of x pretty easily. And then you can even extend it to all powers of x, all right? So here's the theorem. It says let f of x equal x to the power n for any real number n. Okay, the only real number that we would really want to question here is n equals 0, but it turns out it's okay. So I'm just going to leave it. So then let's write that so it looks more like an n. All right, then the conclusion is then f prime of x is always going to be equal to, here we're going to write a formula for this, right? The n comes down, so the new power comes down, and then we're left with x to the new power, which is n minus 1. All right, so the power comes down, we're left with x to the n minus 1. I'm going to put a box around this. I'll do it in orange. All right, so this is our formula. We call this, or at least I call this, the power rule for derivatives. So, it's a theorem. It's always going to work. We're going to take it for granted now. We're just going to believe it. But I'm going to call this the power rule for derivatives. So power rule. All right, let's do some examples to show how powerful this power rule really is. Okay, it turns out it is very powerful. So here are some more examples. Like I said, this rule applies not just to whole numbers, but to any powers, right? So one example of this is f of x equal to the square root of x. This is one that we've done at least once, probably a couple times, using the limit definition. And it's not hard, but it gets, there's work that you have to show. It gets a little bit involved in showing the work. So let's see if we can use the power rule here. Well, to use the power rule, we have to have an exponent, right? So we can rewrite the square root of x as an exponent as follows, right? F of x equals x to the power 1/2. That 1/2 power represents the square root. All right, and once we have this written as a power, now we can apply our power rule. So if this is the function, then f prime of x is going to equal, the power comes down, so 1/2 comes down, x we write down, the new power is going to be the old power minus 1, right? Always minus 1. So I wrote it this way, 1/2 minus 1, but we can actually compute that, right? So we shouldn't leave it like this. So our f prime of x is going to equal 1/2 times x to the power 1/2 minus 1 is negative 1/2. And negative powers, remember, mean to move the entire term to the bottom of the fraction if it's, if it's upstairs. So this becomes then f prime of x equals 1 over 2 x to the 1/2. And we know that x to the 1/2 is the square root of x. That's where this came from, right? It came from up here. So this whole thing now can be written as f prime of x. Our derivative of our function, the square root of x, is equal to 2 square roots of x. All right, so I wrote every step here to do this way. You might be able to skip some steps here, but remember that you're always going to have to show work on a test or on a quiz. All right, so at least show some of this work to show how we got from square root of x up here, square root of x up here. I would definitely write out what that equals here. You can maybe skip to here and then show me that all becomes this at the end. Okay, so maybe just a couple things to write. But this is, if you compare, go back in your notes and compare with when we computed this derivative, the square root of x, using the limit definition of derivative, you'll see that this is exactly the same answer. Okay, so we got the same answer by using this power rule. All right, involved here in this computation, we saw that we got a negative exponent, right? And we saw that, we remembered what that means. But this also gives us an idea of how to do another derivative that we've done by limit definition quite a lot. At least, this kind of derivative we've done quite a lot already in this course, but we can use this. We can do this one using the power rule as well. So what if we started with f of x equals just plain 1 over x? We want to take the derivative of this. Well, it's going to be very similar to the square root of x in that we want to rewrite this as an exponent, so polynomial-like, right? And for this one, there's no power on x, but if there's no power, it's not a 0. It has to be a 1, right? There's an x there, so there has to be a 1. And then it's on the bottom of the fraction, but we want to move it upstairs. So we can rewrite this as f of x equals x to the minus 1 power, all right? And from here, we can do all the same kind of steps that we just did with our square root function. We can apply our power rule now that we've got it in the right form, and then we can unpack that and kind of put it back in the form that we were given, right? So in this case, our derivative, f prime of x, is going to equal, old power comes downstairs, it's minus 1, write the x, new power is the old power, minus 1. So again, I'm writing everything on this one. So negative 1 minus 1. But that means then that f prime of x is equal to negative 1 times x to the negative 2 power, okay? And technically that's the answer. We're done here, right? But let's put it back kind of similar to the form that we got it in, which is with the x in the denominator. And so that is then going to look like f prime of x equals negative 1 over x squared, where the squared power is positive as long as it's downstairs. Okay, so that's how we can use the power rule to help us take the derivative of a function, a rational function, where the term is in the denominator. Okay, let's do one more real quick, kind of based on this idea. Let's combine these two. Let's say, what if we have f of x equals the square root of x divided by x, I'll do x squared this time, change it up a little bit. All right, I want to take the derivative of this function. Well, as of right now, we do not know how to deal with this fraction, okay? We will learn how to take the derivatives of functions that involve fractions, but right now we don't know how to do it, so we can't use any rules that would relate to that. But what we can do is try to turn this into a single power function. So what we can do, I'm just going to manipulate the function itself here, and then we'll take its derivative. But we can start by noticing that square root, right, can be rewritten as an x to the 1/2 power, and just leave the x to the squared on the bottom as it was. And then we can use power rules to combine these two. They have the same base now, right? They're both x to some power. When you divide two things with the same base, you can combine them by subtracting the powers, right? So this can now be written as a single x to the power on the top, which is 1/2, minus the power on the bottom, which was 2. Okay? And if we're going to try to take the derivative of this thing, we should combine this power, right? We should work this out. So this is then going to be x to the 1/2 minus 2 is negative 3/2. So there's our function, right? We haven't taken the derivative yet. We just rewrote this in a different form, which hopefully will make it easier for us to take the derivative. And it turns out it did. Now it's in the power form, right? So now we can write down our derivative, and we can just apply the rule here. So our rule says that the old power comes downstairs, -3/2. Write the x, subtract 1 from the old power to make the new power. So -3/2 minus 1. That's going to give us our -3/2 x to the -5/2. And this time, I'll let us leave this like this because we've made enough changes that it would be really hard to get this back into the form that we were given it. I said really hard. It wouldn't be that hard, but let's just leave it like this because we know that this is accurate. On a test or a quiz, this would be exactly how I want this. So this is perfect. We're going to leave it like this. All right, so now we know how to take derivatives of a lot of functions without, we still had to write some stuff here, but without writing as much and doing as much work as we had to do with the limit definition. All right, any constant, any function that involves just an x, x cubed we use to kind of motivate our x to the n power, and so then any power of x we now know how to take the derivative of. And that's a lot of functions, okay? But it's not everything, and what we need to be able to do is take the derivative of functions that are multiplied by a constant and then functions that have a sum or a difference involved. So I'm going to write down two rules. We're going to use the limit definition again to kind of work out these two rules, and then we'll put it all together to then take the derivative of general kind of sums and differences of any power of x. All right, so here's our rules here. So I'm going to write it as an example again. But let's say that g of x is equal to k times f of x. All right, I want to take the derivative of g of x. So I'm going to take the derivative with respect to x of g of x. So this is equal to, by the limit definition, I'm going to do this at a again. So the limit as x approaches a of g of x minus g of a divided by x minus a. Okay, but then I'm going to plug in the formula for g that we know. Now we don't know, we're going to pretend that we know what f is, and then we know how to take the derivative of f as well. All right, so I'm going to plug that in then, right? So this then becomes the limit as x approaches a of k times f of x minus g of a. G of a is going to be k times f of a. Just plug in a for x, right? All over x minus a. And at this point, we're going to notice that we have this constant k. So I don't know if I made it clear here, but this k is a constant. That's not a function. That's a constant. It's just a number, right? This constant k is common to both of these terms on top. So that k can factor out. And I've drawn it here with the highlighter, showing that it can actually factor all the way out of the limit because the constant, right, the limit does not care about. And so maybe I should write this in slightly more detail since we're just doing it once here. But the limit as x approaches a, I'm going to factor that k out times the limit as x approaches a of f of x minus f of a all over x minus a. All right? And then the point here is that the limit as x approaches a of a constant, we know exactly what that is. That's the constant, right? The limit as x approaches a of f of x minus f of a over x minus a, well, as long as this function has a derivative that makes sense, this is the derivative of f, right? This part right here is f prime. So this ends up being k times, and then all of this is f prime of x. All right? So, this might even seem completely obvious to you guys, but what this means is that when we have a function that is a constant multiple of another function, and we know how to take the derivative of that second function, then we can just kind of factor out the constant and take the derivative of the existing function. So here's how we would write this. We would write the derivative with respect to x of a constant times a function is equal to the constant times the derivative of the function. So the constant can come out, all right? We can kind of factor it out, and then again, our notation for the derivative is that that's just f prime of x. Okay? All right, so we can factor out constants. Now, what about pluses or minuses? So again, I'm going to do the same thing. So let's say, all right, we've got our g of x here. And let's say that this is equal to f of x. I'm just going to do plus, but it turns out this is going to work with minus as well. F of x plus h of x. And in this case, I'm going to say, I'm actually right at this time, f prime and h prime both exist. So they both exist for this function. All right, let's try to take the derivative of g. That's the whole idea here, right? So our derivative with respect to x of g of x, this is equal to the limit as x approaches a of g of x minus g of a all over x minus a. And then once again, we can plug in exactly what g of x and g of a mean, right? So I can write that up here. This is then the limit as x approaches a of f of x plus g of x, sorry, f of x plus h of x. That's all g of x, right? So g of x is equal to f of x plus h of x minus, and then I should put parentheses here, because now g of a is going to be equal to f of a minus h of a. All right, and this is all over x minus a. Okay, and then we can kind of combine like terms here. So I'll do this in pink again. We've got our f of x, or f of a. That's a minus, right? And then similarly, we can do h of x plus minus h of a. Although I have a typo here. I wrote the minus here. I already distributed. That was supposed to be plus, right? G of a is f of a plus h of a. So those are both plus, but that minus is going to distribute. The way I wrote it, it was wrong. So I fixed that. All right, so now we can break up kind of the pink and the green here, and we can write this as the limit. We can write it as two separate limits. The limit is x approaches a of f of x minus f of a all over x minus a plus the limit as x approaches a of h of x minus h of a all over x minus a. And once again, provided these limits exist, we know what they are. So this limit is the derivative of f, that's f prime of a, and this limit over here is the derivative of h, that's h prime of a. Okay, so this one is f prime at a, plus this one is h prime at a. All right, so once again, what we found is that the derivative with respect to x of our sum or difference. So now it's f of x plus or minus. I'm going to write both of them in here. You can work out. So it's a recommended exercise to work out the case when this is a minus sign here. So the derivative of f plus or minus h, this is going to end up being the derivative of f of x, if it provided it exists, plus or minus the derivative of h of x. All right, so taken together, these properties that the constant can come out and the derivative can kind of break itself, it can kind of distribute over sums and differences. So here's our f prime plus or minus h prime of x. So these properties where, again, the constants can be factored out, the derivative distributes over sums and differences, these are properties called linearity. So we say here that the derivatives are linear. All right, we're not going to use this term too much, but you might see it in the text, maybe in some of your other courses that you take moving forward. You'll see derivatives are linear. All right, let's do just one example of this, and then got a couple trig examples that we should do. But here we go. Let's say again, I'll just call this one f again, but f of x is equal to 3x squared minus 9x plus, well, say 14 square roots of x. All right, we want to take the derivative of this. This is our goal, right? So based on these properties of linearity, I'm going to write this kind of in two ways. What we can do is, it turns out it's really nice, is we can just go term by term, and we can really just take the derivatives of kind of the easiest parts of these. So this is I'm going to rewrite this whole thing and then probably switch to prime notation just to make it look nicer and show exactly how we can actually compute this if we were given this on a test or a quiz. So this is what we're asked to do, right? So it turns out what we can do is this derivative is only going to care about the functions, right? Because these are all linear, they're added together, and they obey those two types of rules, right? That the derivative can go over the pluses and minuses and then inside the constant. So this can be written then as 3 times the derivative of x squared, which I'm just going to write as x squared and then in prime like this, minus 9 times the derivative of x plus 14 times the derivative of the square root of x. All right, and so now we can just take these derivatives and put this all back together. So whenever you pull these constants out, you have to remember they have to hang around, right? So that 3 has to hang around. The derivative of x squared is going to be 2x. That's just following 2x to the 1 to the first power, so 2x. That's just following our power rule. Then we have our minus 9 times derivative of x. We said above earlier in this lecture that the derivative of x is 1, so that's times 1, plus 14 times the derivative of the square root of x, which we could work out again, right? But we've already done it, right? So let me scroll up. It's an advantage of keeping my notes here. The derivative of x squared is 1 over 2 square roots of x. We found that in this example here, right? So going back to our current example, we can just write that down, right? We can take advantage of that. So 1 over 2 square roots of x. And now we just have to kind of clean it up, right? Combine some like terms, make it look nice. So this is then going to be 6x minus 9 plus 14 over 2 can just be written as 7 over the square root of x. And so this is our function f prime. This is the derivative of the given function. Okay, so we can apply all these linearity properties all at once. The power rule and the linearity properties can all be applied together here. Term by term. That's really, so when you think of linear up here, I wrote it up here, right? When you think of linear up here, just think of term by term. We can really just break down our derivatives term by term as long as they're added or subtracted. If the terms, the functions are multiplied or divided, we saw this one example up here where we had to do some more work, right? The square root of x over x squared, that required us to do a little bit more work, be a little more careful. That's fine, okay? But notice it's not linear. That is not linear. We had to do all the combinations algebraically, and then once we got it using correct algebra to a form that fit our rule, then we could apply our power rule at this step, right? We couldn't do it before that, though. All right. So there's two more functions that I want to take the derivative of in this lecture, and then we'll leave it here until the next lecture. But actually, I'm only going to do one of them, and then I'm going to leave the second one as a recommended exercise. But these are our trig functions, okay? So trig derivatives. Before I actually write, and I'm only going to do 2 of the trig derivatives. I just told you I'm only going to do one of them. Now I've said it a couple times. But the trig derivatives, I'm going to do one of them. And to do it, we need an identity, okay? Sum or difference formula. So this one, I'll just write this. We need this identity. All right, so this identity is sine of x plus h. This is going to show, we're going to take the derivative of sine together, and then I'm going to leave for you guys the derivative of cosine as a recommended exercise. But sine of x plus h, this is, again, I believe it's called the sum or difference rule of trig functions. This is going to become sine of x times cosine of h plus cosine of x times sine of h. Okay, so sine does not itself distribute over a sum, does not distribute and become sine of x plus sine of h, but in a way it kind of distributes when you involve the cosine as well. Okay, you guys for your recommended exercise will need the following here. So cosine of x plus h. This one equals cosine of x times cosine of h minus sine of x times sine of h. Okay, so these are our sum or difference formulas that we will need. There is one more formula. There are 2 more formulas that we will need for this, and these are 2 limits actually that one of them we did in recitation. That was this. The limit as h approaches 0 of sine of h divided by h. So in recitation, you did this with a theta instead of an h, and you made a geometric argument to show that this is always going to be equal to 1. So the limit as h approaches 0 of sine of h divided by h is always 1. All right? And then the other limit that we need is the limit as h approaches 0 of cosine of h minus 1 over h. And this, it turns out, is always 0, this limit. So for this example, we're going to need both of these. And again, when you work out your recommended exercise, you're going to need both of these as well. And by the way, be prepared to work out this derivative of cosine of x plus h. Be prepared to do this on a quiz, okay? The derivative. I underlined that and said be prepared to do this formula. You don't have to prove this sum or difference formula, but you have to be able to use it, okay, to take the derivative of cosine. And let's just do the derivative of sine here, and then you'll see why. So again, our example here is if our function is equal to sine of x, we want to take the derivative. So then f prime of x is equal to the limit. This time I'm going to finally use our h definition of derivative, which we haven't used yet today, but this is the limit as h approaches 0, f of x plus h minus f of x divided by h, right? And we're going to plug in the sine function. So this becomes the limit as h approaches 0. And now you see why we need that first sum or difference formula, because it's going to be sine of x plus h minus sine of x, and then this whole thing divided by h, okay? So the next step then is to apply that sum or difference formula. So this limit becomes, remember, when you write these limits down for derivative, when you use a definition of derivative, you're always going to get 0 over 0 if you wrote it down right, okay? It's how that definition of derivative is built, basically. It's always going to be that way. So this now becomes a limit as h approaches 0 of sine of x times cosine of h plus cosine of x times sine of h. That's exactly the formula that we wrote down. Minus sine of x, all divided by h. Okay, so now what we want to do is factor some like terms here and just try to get this thing kind of simplified a little bit. And basically we can see we have a couple like terms. So the like terms here are sine of x right here, and really that's it, right? But what we can do is we can kind of divide up, if we kind of group these terms together, try to circle just these, group these terms together and leave the other one separately, we can break this into two different limits. We can write this as the limit as h approaches 0 of sine of x times cosine of h minus sine of x again, all divided by h, plus the limit as h approaches 0 of cosine of x times sine of h, all over h, like this. All right, and then we can actually go through and factor out the sine of x. So let me get this. The sine of x can get factored out from this one. All right, and then once it's factored out, it can come all the way out of the limit like we talked about before, but let's write it out in two steps here. This becomes limit as h approaches 0 of sine of x times cosine of h minus 1 divided by h, plus the limit as h approaches 0. For this one, I'm going to write it very similarly. Cosine of x times sine of h divided by h. And importantly, what I did here was I left these terms that do not have an h. I left them kind of out of the fraction that's going to be limited, right? Because both of those, since they don't have an h, they can come right outside the limit. The limit is going to treat those like those are constants because they don't have any h's. So as h changes, the value of sine of x will not change, right? And so then what we end up with is we have sine of x times this limit as h approaches 0 of cosine of h minus 1 over h plus cosine of x times the limit as h approaches 0 of sine of h over h. And these are exactly the two limits that we were given, right? So the limit as h approaches 0 of cosine of h minus 1 over h, that whole thing becomes 0. And the limit as h approaches 0 of sine of h over h, that one becomes 1. So this whole thing then becomes sine of x times 0, because that limit is 0, plus cosine of x times 1, because that limit is 1, and then all that's left here is cosine of x. So, to summarize here, for our function f of x equals sine of x, we use the limit definition, and we computed that the derivative of sine of x is cosine of x. Okay? So, and we use the limit definition, so we prove that basically. We don't have to do that again. We don't have to use the limit definition again, unless we're told to on a test or a quiz. But in general, the derivative of sine is always going to be cosine. All right, the recommended exercise, using that information that I left us there at the beginning of this problem, the recommended exercise is to compute the derivative, of cosine of x. It's going to be very similar, except the sum or difference formula is different, right, for cosine than it is for sine. So when you plug this in and you follow all the same steps, again, you'll have to do this on the test and or quiz, then what you will find is that, showing all the work, make sure you can do this, that f prime of x, the derivative of cosine, is actually minus sine of x. So the derivative of cosine is negative sine. Okay, so recommended exercise, that's what RE means. Recommended exercise, make sure you can do this one, work out all the details, and I'll see you guys in the next lecture.